The recurrence equation that we need to solve is T of n is equal to 3 times T of n by 3 plus some constant c multiplied by n. We can assume that this constant c is some positive number. So we are going to use the recursion tree method, which we used earlier for the merge sort algorithm analysis. We start building the recursion tree from a single node. That single node is T of n. What we will do in each step is we will replace T of n or T of n divided by some number b when we are dealing with subproblems. We will replace these t's with their corresponding values as given by the right hand side of this recurrence equation. But we won't simply write the right hand side in a linear fashion like this. We will represent it diagrammatically. So T of n will be replaced by c times n with 3 children, T of n by 3, T of n by 3 and T of n by 3. So we are going to write the function c times n or f of n in general in place of T of n, and we are going to write the expressions for the running time on the smaller subproblems as children of this expression or c times n. So this is the tree that we get after the first round of applying this recurrence equation. Note that the value of T of n is the sum of the values of these 4 nodes. T of n is c times n plus T of n by 3 plus T of n by 3 plus T of n by 3. So we are just rewriting this equation in a diagrammatic form. We can do the same by expanding these 3 nodes further to create one more level. So what is T of n by 3? If T of n is given by this expression, then T of n by 3 can be obtained by simply replacing n by 3. Replace n by 3 on both sides. T of n by 3 is going to be 3 times T of n by 3 divided by 3, which is n by 9, plus c times n by 3. So when we open up the recursion for these 3 nodes, we will get in the next step c of n, and we will replace this T of n by 3 by c times n by 3 with 3 children, each being T of n by 9. And likewise, the other 2 children of c times n will be c of n by 3, and they will have 3 children, each being T of n by 9. Again, the value of T of n, which was the sum of the values of these 4 nodes, is also equal to the sum of the values of all these nodes. One node at the first level or at the 0th level, 3 nodes at the first level, and 9 nodes at the second level. So there are 3 nodes here, there will be 3 other nodes here and 3 other nodes here. In the next iteration of the recursion tree method, we will open up these nodes by replacing them by their values on the right, as given by the right hand side of this recurrence equation. So T of n by 9 is equal to, we can replace n by 9 on both sides. So we get 3 times T of n by 9 divided by 3, which is n by 27, plus C times n by 9. So each of these T of n by 9 nodes will be replaced by a subtree C times n by 9 with 3 children, T of n by 27, T of n by 27, T of n by 27. So imagine replacing each of these T of n by 9 nodes by this subtree. And by that we'll create another level in this overall recursion tree. So if we keep doing this, if we keep opening up the values of T on smaller and smaller and smaller subproblems until we hit subproblems of size 1, that is where we'll stop. So we'll keep creating more additional levels of this tree by opening up the recurrence equation for these T's until we'll end up with leaves, each of which will have the value T of 1. So what will a snapshot of the recursion tree look like at that stage? Well, we'll have C times n as the root, C times n by 3 at the first level, and then C times n by 9 at the second level. So there will be 3 children of each node here, each having the value C times n by 9. Each of these nodes in turn will have 3 children. Right? If you open up T of n by 27, we are going to get 3 times T of n by 81 plus C times n by 27. And we write C times n by 27 here, and then we'll further divide it into 3, further have 3 children for each. So this is going to continue until we hit the bottom, and we'll hit the bottom when all the nodes that we have are T of 1. Note that the subproblems are decreasing at the same rate along all the paths in this tree. So we will hit T of 1 everywhere uniformly. So if we call the top level as level 0, this level as level 1, this level as level 2, this one as level 3, then at the ith level we are going to have subproblems of size. So at level 0 we have a problem of size C times n. At level 1 our problems are of size C times n by 3. At level 2 our problems are of size C times n by 3 squared. At level 3, our subproblems are of size Cn divided by 3 cube. So at level I, our subproblems are going to be of size, uh, our nodes are going to be of value Cn divided by 3 to the power I. And how many nodes will there be at each level? Well, if we are dividing each problem into 3 subproblems, then each of the nodes is going to have 3 children. So the number of nodes at the top was 1. There was only a single node at the topmost level. At level 1 we had 3 to the power 1 nodes, 3 nodes. At level 2 we had 3 to the power 2 or 9 nodes. At level 3 we had 3 to the power 3 or 27 nodes. At level I we are going to have 3 to the power I nodes. And if we call the bottommost level as level h, h denoting the height of the tree, then our subproblems are of size 1 at this stage, except that we are writing them as t of 1 because we are not expanding t of 1 further. Okay, so that's where we stop. And we are going to assume that t of 1 is some constant. If the argument or the size of the subproblem is a constant, the running time is also going to be a constant. It's not going to be a function of n if the size of the subproblem is small enough to be some constant. So the number of nodes at this level will be 3 to the power h. Now how do we evaluate the value of t of n? We do so by summing up the costs at each node at all the levels in the recursion tree. And the way we sum up these costs is level by level. So we'll add up the costs at level 0, then we'll add up the costs at level 1, then we'll add up the costs at level 2, at all the nodes of level 2, and so on. So if I call these as level sums, at level 0 we have a single node with cost c times n. At level 1 we have 3 nodes, each of cost Cn by 3. 3 times Cn by 3. And so the sum of the costs of the nodes at level 1 is Cn. The sum of the costs of the nodes at level 2 is 3 squared times Cn by 9 or 3 squared, which is again Cn. At level 3 we have 3 to the power 3 nodes, each with cost Cn by 3 cube, which is also Cn. At level I we have 3 to the power I nodes, each with cost Cn divided by 3 to the power I, which is Cn. You can see that the level sums are the same for every level. At the very last level though, we will have 3 to the power h nodes, and the cost of each node is not given by an expression in terms of c because we are not opening up t of 1 further. So we can just write this as 3 to the power h multiplied by t of 1. And t of 1 is some constant, let's say it's some constant k. The previous level, level h minus 1, will have 3 to the power h minus 1 nodes, each with cost Cn divided by 3 to the power h minus 1. And that's also going to be Cn. Now, what is the value of h? What is the height of this tree in terms of n, the number of, the size of the subproblem? Well, if you look at this path over here, you can look at any path, but let's just focus on this path. The number of the size of the subproblem is reducing by a factor of 3 at every successive level. So we start off with a problem of size n at the topmost level. When we created the next level, we had subproblems of size n by 3. When we created the second level, we had subproblems of size n by 9. When we created the next level, we had subproblems of size n by 27. So we went on creating smaller and smaller subproblems until the size of the subproblem got reduced to 1. So if the size of the subproblem at level I in general was n by 3 to the power I, and therefore at level h, the size of the subproblem should have been n by 3 to the power h. We are saying that h is the height of the tree, or the level at which the size of the subproblem becomes equal to 1. So if we equate n by 3 to the power h to be equal to 1, we can get the height of the tree in terms of n. So this means 3 to the power h is equal to n, or the height of the tree is log n to the base 3. Now we can write an expression for t of n which is the sum of all these costs at each level. So the cost at levels 0, 1, 2, 3 and so on until level h minus 1 is c times n. And the cost at level h was 3 to the power h multiplied by some constant t of 1. Now we have computed h to be log of n base 3. So t of n, which is going to be 3 to the power h multiplied by t of 1 plus cn plus cn plus cn plus cn from levels 0 to h minus 1. So we're going to add cn to itself from levels 0 to h minus 1. So there will be h such terms, cn, and from levels 0 to h minus 1. There are h such terms, and at the very last level, level h, we have a cost of 3 to the power h multiplied by t of 1. Now if we replace h by log of n base 3, we get t of n is 3 to the power log of n base 3. So 3 to the power h multiplied by t of 1 plus cn. So cn is not dependent on the level number. So we can pull out cn and we'll be adding cn to itself h times. And so we can call this as Cn multiplied by h, but h is log of n to the base 3. Now we can simplify this expression. 3 to the power log of n base 3 is nothing but n. Right? 3 to the power log of n base 3 is simply n. So n multiplied by t of 1 plus Cn multiplied by log of n base 3. So if this is the expression for t of n, then we can see that t of n is in theta of n log n. This is the dominant term. T of 1 is a constant, so this term is a lower order term. And so T of n can be said to be in theta of n log n. Note that the asymptotic complexity of the algorithm whose running time is given by this recurrence equation. This could very well be a modified version of merge sort where we are dividing the original problem into 3 subproblems, each of size n by 3. The asymptotic complexity has not changed. It's still theta of n log n, which is what it was when we had 2 subproblems, each of size n by 2. So we haven't improved the asymptotic complexity by dividing the problem into 3 subproblems instead of 2 subproblems. You can try as an exercise dividing the overall problem into 4 subproblems or 5 subproblems, and in each case you will find that the asymptotic complexity remains theta of n log n. One of the points to note here, which will you'll see this appearing as a pattern in the other examples we take as well. T of n was ultimately written as the sum of 2 expressions, first of which was the number of nodes at level h multiplied by t of 1 plus a series having h terms, one term for each level from 0 to h minus 1. And what is being added here is the level sum, or the cost, the sum of the costs of the nodes at each, at all the nodes in each level. So within each level, the sum of the costs was c times n, and that is being added within this series. Now this series here happened to be a very simple series because c times n was a constant, and so we could pull it out and we simply got Cn multiplied by h. So this was a constant series. Okay, adding these h terms was equivalent to adding the same term h times. You'll see in other recurrence equations that we can get more complicated summations over here. We could either get a decreasing geometric series or an increasing geometric series. This was not a geometric series, or one can think of this as a geometric series with the common ratio 1. So every term of the series had the same value. But in other examples that we're going to take in the next few videos, you'll see that we could get we're going to get in general a geometric progression. And the reason I'm pointing this out here is that if you keep an eye on this overall expression, you will see some patterns, and those patterns are going to help us derive an expression for T of n in general when we have A subproblems of size n by b with a cost of f of n in combining the solutions to those subproblems.